Hi, good morning and good afternoon to everyone. Very excited to be here to talk about pressure regulation with two of the brightest minds in the irrigation industry. Um, Rick's laughing, and I'm talking about you, Rick, and I'm talking about you, Alex. So we'll get started here in just 2 or 3 minutes, but I'd really invite everyone who's on today to feel free to drop in the chat, let us know where you're joining from. We'd love to know what you're working on today, and really just excited to get started here in just a couple minutes. And Rick, Alex, why don't you guys go ahead and tell us where you're joining from? Oh, hey, Paul, good to see you joining us from Florida. Rick, one of your neighbors there.
Yep, I'm also in Palm Beach County, Florida, down in South Florida.
And Alex, you're joining us from the Heartland, right? You're up in
Yeah,
Oklahoma.
I am joining from small town Humphrey, Nebraska. Working with work for Valley Irrigation in the water applications department, and just excited to be involved and talk about some pressure regulation today.
Awesome. Oh, Kelsey, Oklahoma City, that's where I'm joining from as well. Love to see a couple of folks from Oklahoma. That's great.
California, Ohio, Colorado. It's nice.
Really, really nice to see everyone joining us from across the country. Just another reminder of how invested our industry is into continuous improvement and education. So love seeing this. All right, two Oklahomans. That for me is a personal record for a webinar that we've hosted. So I'm really pleased to see that. Really glad to see some Okies on the webinar today. And
Yes.
with that, I think Rick, Alex, if you guys are ready, we'll go ahead and get started. Does that sound good?
Yeah, absolutely.
All right, fabulous. Well, I'll just really briefly introduce myself. I'm Luke Reynolds. I'm the Associate Director of Government and Public Affairs for the Irrigation Association. Today, we're going to be doing a deep dive into pressure regulation and the future of efficient irrigation. And I said it once, I'll say it again. We're joined by two of the brightest minds in the irrigation industry to discuss pressure regulation. And just to give everybody a kind of a heads up of how we'll manage today's webinar, really want to encourage you to use the chat function as we go throughout the webinar today. Ask questions, and I can't promise that I'll stop the webinar based on any question, but we'll try to get to as many questions as we can, both during the webinar and then towards the end. And I would also say that we're going to spend the first half of our webinar talking about pressure regulation and landscape applications. We're going to spend the second half of our webinar talking about pressure regulation in agriculture applications. So with that, Rick, Alex, I'd love to give you guys a minute or two to introduce yourselves, and then we'll turn it over to you, Rick, and you can get started.
Okay, well, then I'll start. My name is Rick Hall. I'm with K-Rain Manufacturing. I've been fortunate enough to be in this industry now for a little over 35 years, the last 20 of that in manufacturing. And the great thing is it's brought me literally all over the globe. So I've, again, had the benefit and the pleasure of working with contractors, distribution, manufacturing, just about everybody. So super excited to be here and share what I can.
All right, yeah, my name is Alex Schumacher. I've been in the irrigation industry for about 12 years. The first half of that was with Lindsay Corporation, or Zematic, for center pivot irrigation. And the second half of that has been with Valley. So just been focused on that manufacturing side, and been in water applications that entire time.
All right, awesome. Thanks very much. Emil, if you want to go ahead and move us into Rick's portion, we'll go ahead and get started.
Okay, so pressure regulation. So when I travel and I speak to people, it's every now and then you'll get that question like, what is the number one variable? What is the number one concern when it comes to irrigation? And there's a lot. But interesting enough, with all the decisions that we have in making up an irrigation system and all the components that are involved in that, a lot of them you can make a decision. You make the right decision, you can move forward. But the one variable that changes on us all the time is pressure. And we all know that our water delivery devices require pressure to work, assuming we have the available water. So how do we control that? How do we make pressure our friend as opposed to it being a disruption, happening and creating issues where we thought we had what we thought we had, and we end up with the pictures that you see on the right. So let's talk about some of those basic failure modes, some of those things that we address when we think that we have adequate pressure. So high pressure atomization, that top picture you see there, where your sprays and even rotors tend to be like big fogging devices as opposed to water delivery devices. So when we talk about water delivery, we're basically talking about the water droplet size, right? Controlling those water droplets and dispersing them evenly or uniformly over our irrigated area. So we need to control the pressure, right? There's a couple of more illustrations there of a pop-up spray. Probably the one on the left is what we're looking for. That's more of a controlled discharge, where on the right, that's probably a little low. And certainly that bottom picture you see there of single stream rotors basically look like water features, throwing water from point A to point A. They don't have that fallout. They don't have that, what we call distribution uniformity. So when we deal with pressure and our water delivery devices, we want them to be uniform or optimum, right? We don't need a high or an overpressurization, and we certainly don't want a weak or an under pressure distribution. So we have to take the pressure into consideration both in our design, our installation, and the actual operation, right? So in the design part, we need to take the site condition. What are the things within the site condition that can affect our pressure? How can I use it to my advantage and not a disadvantage? How is it going to affect my precipitation rate, right? How we're putting the water down. Incorrect pressure regulation can cause a problem, right? If we think that we're solving an issue in one area by controlling the pressure, and then it fights against us in another area. And then, of course, our run times. How do we schedule the run times? Run times, we have a thing called scheduling coefficients, right? Where we've done everything that we can possibly do, but we've got to modify the run times or increase the run times to account for all these different inefficiencies. So pressure regulation is super, super important in trying to control that. So let's go to the next slide. Let's talk about some of this. So the failure modes. So what are we talking about? Site conditions. This is exactly what we're talking about. Elevation changes are huge, right? We talk about we can lose pressure in every single device, every linear foot of pipe, the type of pipe, the size of pipe, your fittings, your water delivery devices, backflow preventers, the meter itself, valves, all these components actually rob us of pressure. Well, the one variable that a lot of people seem to overlook is the changes in elevation. Water has weight, right? It has weight, so therefore it creates pressure. You may have heard, a lot of you, that for every elevation change, every foot of elevation change, our pressure is either going to increase or decrease almost a half a PSI, 0.433 to be exact. So this is one example of where pressure regulation becomes critical, right? Look at the little example we have there. I've got a working pressure or a pressure there of 40 PSI. That's at my valve. Now, I'll ask a lot of people when they have issues with an irrigation system, what pressure do you have? And often, a lot of times, they'll tell me what their point of connection pressure is or what their static pressure is. And they don't understand why they're not getting good water or extremely high pressure at the end of the line. So here's a little example or an illustration to tell you that. 40 PSI at our valves. Well, to the left of that, I've got water meter, backflow device, zone valves, pipe. In order to get 40 PSI, if we go upstream to our point of connection, we're going to have a lot more pressure than that, right? So an example, if I have a, for the water meter, if we had a 5/8 water meter delivering our zone sizes were, say, the mid-teens, you could lose 8 to 10 pounds of pressure just to that water meter. What about a backflow device? Say I had a 1-inch RPZ, again, delivering to the zones in the mid-teens. We're going to lose, 10 or 12 pounds of pressure there. How about the zone valve? I had a 1-inch zone valve. Again, depending on the valve, the make, the model, in that mid-teens, you could lose a couple of PSI there. And then of course the pipe. And this is usually a big one where people get lost. If I had since this is going to be a smaller residential or an average residential system, and I'm using a 1-inch, let's say scheduled 200 PVC pipe, in the mid-teens, 100 feet of pipe, I could lose 3 PSI. What if somebody put in 3/4-inch pipe thinking that, well, a smaller pipe builds pressure? No, it does not. It increases velocity, but it robs you of pressure. And that 3 PSI that I just mentioned for 100 feet of 1-inch pipe goes to about 10 PSI. So there's where you lose a lot of pressure. So add up these examples I just talked about, that's about 27 pounds of pressure. So my point of connection pressure or at the water meter would have to be around 67 PSI. That's the one loss. Here's the second loss in this illustration: elevation changes. In this example, if I go uphill based on that 0.433 PSI for every foot, that 40 PSI becomes 29 PSI. Same token, if I had on that same system, but at a different zone, a downhill drop of 25 feet, I'm going to gain pressure, that 0.433 PSI, which means my pressure goes to 51. So this is what confuses people on a job site where you have a pressure, you think it's 40 PSI, but in one part of the site, it's 29, and another part of the site, it's 51. If we look to the left, this is a nozzle performance chart that everybody's probably familiar with. This happens to be a rotor with a 3 gallon per minute nozzle, pretty common discharge. Well, look how those rotors are going to operate differently on those different pressures. If I had a rotor at the top of the hill at 29 PSI, what are we looking at? About 35 and a half feet, about 2.5 gallons of flow. But a rotor on that lower elevation getting 51 PSI, that same rotor, that same nozzle is going to deliver about 38.5 feet as far as the radius and about 3.2 gallons per minute. Look at the precip rates to the right on both of those. Am I putting the same water down? Am I going to have the same run times? Absolutely not. So here's where pressure regulation can kind of help us to make sure that we evenly disperse the water through all the heads, through all the zones. Let's go to the next slide. So where do these components live? You've got a lot of different options, but it depends on where you are with the irrigation system. If you're on the design side and at the very beginning, then I might be, and I'm taking in consideration elevation changes by controlling my pressure differences through pipe sizing and things like this. I have the option of selecting all my components and installing the right pipes and stuff like that. Then I might want to go with the whole system pressure regulation like you see there in the top left, where I have one pressure regulator that controls a high pressure distribution to my system. If I don't have an option on the early design size or the install, I'm inheriting this property, I might look at just simply replacing the valve. I could actually put an inline, there's an example on there to the right, an inline pressure reducer. On the lower left is a valve with a pressure regulator built into it. So I can control that high pressure situation or that pressure at the beginning of the zone, assuming that my pipe sizing and my pipe runs and stuff like that aren't going to rob me of more pressure. You might want to hit the next button. I think there's another picture for this thing. There we go. But then again, you might not have any knowledge of any pipe, the main, the laterals. You have no idea what's in the system. You just know the water delivery devices, what's actually spraying the water. So here's where we can control pressure, single application right at the water delivery device. We manufacturers make rotors with pressure regulation, spray bodies with pressure regulation, which has become requirement in a lot of states now. We even have nozzles to help build these efficiencies in the distribution uniformity and even pressure regulation. So where you choose to put your component has to do with how much you know about the site, how much control you have over the site. Let's go to the next slide. So what if, again, let's assume that it's safe to assume we don't know what's underground. We have no idea what type of pipe, what size of pipe, even how the pipe is run. So I don't even know how to calculate the links, even if I dig little windows to find out what type and what size the pipe is. or I don't know how to make all these different calculations, or I don't have the time to do all the calculations. There's a couple of useful little tools that we can use in the field, gauges, in order to gauge what that pressure is. And those are the gauge you see to the left that you're going to use for sprays, where you actually remove the nozzle off the spray body, off the spray riser. You twist on this gauge, and then you put the spray nozzle on top of that fitting of the gauge, turn the system on, and there's our pressure. More importantly, it's our dynamic pressure. You know, that nozzle performance chart that you saw a slide ago with the rotors, the pressures that are listed on there from every manufacturer are dynamic pressures, not a static pressure. It's what much pressure is at that head that's being delivered when it's in operation. These gauges tell you that. Another gauge you use for rotors, the one picture to the right, is a gauge with a pitot tube. And the pitot tube allows us to actually check the pressure, the discharge of that nozzle, so we know exactly what the dynamic pressure is. And there's two different pictures there. The picture of the pitot tube you see in the lower right is being used in that picture to the left. On the top, we just have a hose that extends from the pitot tube to the gauge. So you're not quite getting as wet. It's easier to read. You can get a buddy, whatever the case may be. But these gauges, I can go around the site, go around the zone, vary in different elevations. I can go directly to the water delivery device and see exactly what my pressure is. Now, if I know my pressure and I know the nozzle, I can look at the manufacturer's nozzle performance charts, and it's going to tell me exactly what the radius is and what the discharge is. So a quick and simple way of knowing exactly what you're dealing with, as opposed to when you're asked how much pressure you have, you give I got great pressure. You know, let's know exactly what it is. So let's go to the next slide.
Hey, Rick, just real quick before we jump into that, we've got a great question from Darren.
Absolutely.
Thanks for that question, Darren. I thought it might give you a second to catch your breath, Rick. That's a ton of great information, and you're doing a great job on the timing of all of it. So thanks. Darren asks, what about the use of ACVs, automated control valves, that open under low pressure and close under high pressure? So let you speak to that, Rick.
Yeah, so again, it's another tool of making sure, and that's a good question because it kind of goes to what I've already mentioned. There are a lot of tools. We're not going to talk about them all today. We have limited time, but there are a lot of different innovations and components that are available to the installer today that we didn't have years ago. So absolutely, the best advice I can give you is understand the site that you're trying to control, that you're trying to manage, or you're trying to design, and then use the appropriate component that helps you make pressure your friend and not your foe. Everybody
needs more friends, right?
Everybody needs more friends.
One more quick question, and I'll take this one. Stephen Muir asking, thanks for the question, Stephen. Is there an industry manual or list of pressure regulated sprinkler heads that meet a certain spec for efficiency? Really great question. And Rick, I'm going to let you kind of speak to this as well from the manufacturer perspective. But Stephen, I can speak from our perspective. At the IA, we have historically put together as comprehensive as we can list of sprinkler heads through one of our publications, Irrigation and Lighting. So I'll try to provide that in the chat. But Rick, do you want to speak just to maybe about how K-Rain distributes that type of information, the efficiency information for heads?
Yeah, it's so every manufacturer has offered more efficient products where they're constantly in development. It's something we work on every single day. You know, the challenge that a manufacturer has is we're developing products that are being used essentially all over the world. So the more options that we can provide you gives you more tools that you have available to you to make the right choice for your situation. And we're actually going to talk about in the next slides or so ways of doing that. You know, I don't know if anybody here has ever done an audit, but there are ways of matching your data and choosing the correct component. And if you inherit a system and you're talking about swapping out components, there's a system quick little audits that can be performed. So you can decide what component needs to be replaced, whether it be a valve or the individual water delivery device or what. So hopefully I answered that question all right. If not, let's move on to, okay, so this slide. So installation and maintenance. So here are some of the considerations that we have to take when we're installing a system or maintaining a system. The first one is kind of a duh, the orientation. Remember, all these things have an inlet and an outlet, so you got to make sure, like a valve, you're not installing it backwards. You have to understand its regulation. I see a lot of installations where a pressure regulating device has been installed because they really didn't understand the pressure that they're working with or the device that they chose. And I end up not even having the pressure that you chose at the water delivery device. For example, I need to maintain 40 PSI, or I need 40 PSI at the water delivery device. So I chose to install a pressure regulator that regulated the pressure or kept it to 40 PSI. And I do a check at that device, I don't even have 40 PSI. So we got to make sure that we, again, selecting the right unit and making sure that its installation is correct. Also, grit and sensitivity. This is a component not unlike any other component. Putting a filter on a system to make sure that if I've got a lot of debris or contamination in my system, that I'm filtering that out and not losing the effectiveness of my pressure regulation. And then I also have to take and consider seasonal checks, right? I've got to maintain the system. Pressure can change, right? Especially in some of these developments where the infrastructure demand is getting more and more and more because of population growth, more houses, and the pressure that I had a year or 2 years ago, I don't have today. So my pressures can change with the seasons and with population growth and even maturity of plant material, right? So let's go to the next slide. See if we can't wrap this up and give Alex a go at this. So here's this little mini case study I wanted to do to kind of put all this into perspective. We've all probably seen this and maybe wondered what this is. This is an audit. We're putting out catch cups. You may have heard when I say turf zone, and I've got DULQ there, distribution uniformity in lower quarter. This is almost like if you've ever heard somebody express precipitation rate, both gross and net, right? Gross precip is basically what the water delivery device is projecting and throwing into the air. Net is what actually lands on the ground. So your plant material doesn't care about the gross. It doesn't care about what's being thrown into the air. It cares about what actually lands on the ground and gets to the root structure. So when we talk about distribution uniformity, controlling our pressure so our water delivery devices can not only give us 100% coverage over the irrigated area, but do it uniformly. And uniformly doesn't mean 100% coverage. It does, but it doesn't mean that we're getting 100% even coverage. So we look at DULQ. We look at the entire wetted area, and then we look at the smallest 25%, right? We want to know what's the driest area out of that entire coverage, because my turf is going to react to that, right? If it dies in that 25%, that's not good. Your customer's going to say there's areas of my irrigation that my system that's dying. The same token, that means that there's a larger area that's getting too much water. So we're wasting water. We're taking away the efficiencies. So if I look at this, let's take it one step further, go to the next slide. And here's what we're talking about. So the illustrations to the left, this is what we typically see in a system where we're not really controlling our pressure. There's no pressure regulation in here. And if I look at the discharge to the heads to the left, closest to the valve, I've got a lot of discharge. But because I'm losing pressure as I go down the lateral, as I go further into the zone, my discharge gets less and less, right? When we look at the nozzle performance charts that every manufacturer provides, and you look at a particular nozzle, the higher pressure is going to deliver more water, right? It throws it further and delivers more gallons per minute. If I have lesser pressure, the discharge drops, right? Both my radius, the distance, and of course the flow. So the top illustration is showing you what happens without pressure regulation. The right is showing you what happens with the little catch cups. That's your uniformity. That's how the water is being applied to that irrigated area. So if I drop down to the bottom and I regulate that, if I put pressure regulation in, the correct pressure regulation in, and I have a nice even discharge, The illustration to the right tells me what I'm now collecting in those catch cups. There's my uniformity. It's nice, it's even, it's consistent. So let's go to the next slide. And let's look at that in what we call a densogram. Whoops, kind of missed a slide, I think. Go back. Okay, go forward. One more, one more, one more. Oh, we're missing a slide. That's a shame. Oh my gosh. All right, the next slide. So let's back up. Let's go back to the slide we were at previously. The slide we're missing is I took that illustration to the right and I gave you a picture of the zone in what's called a densogram. It colored the entire area. And if you can envision a big oval, if we put an oval over top of that, I'd have lighter blues on the right side. And the further that I got to the left, where I'm getting more and more water from the non-pressure regulated side, that color would get darker and darker and darker because it's getting more water, right? So the problem with uneven watering, Luke, are we still live? We good?
Yeah, we're good. We're just updating that slide so you can demonstrate it.
Okay, perfect, perfect, perfect. So I'll tell you guys real quickly what happens then if I don't have even watering. If I've got this super overwatering on the one side of the zone and then underwatering the other side of the zone, what happens then at overwater side? Well, obviously inefficiencies. So I'm having to put more water or more energy if it's a pump to irrigating that area. And that overwatered area is what's going to create a problem, right? We can get landscape damage from that. Let's say that the irrigation system ran, it really saturated part of the turf. The mowing crew came, ran the mower over that wet area and start putting ruts in. So it starts damaging the aesthetics and damaging the landscaping. Overwatering causes a lot of problems as far as pest infestation or fungus like brown patch or root rot. You can get nutrient leaching where you're literally just flushing out the nutrients of the soil that plant material. Beautiful. Thank you very much. And then, of course, the poor aesthetics, which I talked about, the lawnmower running over or erosion, or I don't know, people that are in a high clay content. You see, you know, young trees, small or shrubs or whatnot being planted and then they stake them. You know, I've seen some high clay content like in the Atlanta area where I've seen new installs, a heavy rain, a little wind, and the whole thing just kind of rotates. The root ball becomes like a ball in a socket in the ground from the overwatering. And then, of course, maintenance cost. You know, all those damages that I listed there can start to run up a bill, right? We've got to repair these systems. I've got plant material that is going to start to die that I need to replace. I've got treatments I got to pay for to help put the nutrients back in the ground or deal with the funguses, the pest control. So you can see that overwatering creates a big, big problem. But what's controlling my run times is the underwatering, right? I don't want to get dead landscaping in the zone. So my run times are based on getting enough water that underwatered area is nice and green, but I can't control the run times on the other side. So this is where pressure regulation can eliminate all that and kind of level it out. So if there's some questions, we can certainly get to those, but I want Alex to have a time to talk about how pressure regulation is affected on the agricultural side. So Alex, it's all you.
Well, I'm going to hit pause real quick. We're going to give Emil, my colleague Emil, just a sec to switch slides here. And we've got a ton of great questions. So Rick, if you don't mind, if you still got a few words left in you, let's go through a couple of these questions while Emil's getting us set up. So let's start with Scott Reagan's question. How do the number of heads on a zone impact the pressure to the last head? And I'll be honest, this is going to be our lightning round. So as quick as you can, Rick, that would be great.
Yeah. It affects it a great deal, right? If I've got 10 heads on a lateral and it's a single lateral, remember, every foot that the water travels to that pipe is robbing you of pressure. The other thing is the available water. So if I've got, let's say, 15 gallons of available water to that zone, and I put 10 heads and they're 1 gallon per minute nozzles, well, I'm only pulling 10 gallons out of the 15. Probably easier to control the pressure. But if I've got 10 heads with 2 gallon per minute zones, that's 20 gallons. I don't even have enough water. Your dynamic pressure is going to drop to nothing. So yes, the number of water delivery devices and the nozzle size. First, we can't exceed the available water, then you control the pressure.
Great answer. All right, moving right along. Andrew Fleet, thanks for this question. Andrew asked, and I know this is a question related to kind of the locality that I'm in. We've got explosive residential growth kind of outside of folks who can tap into the city water. So Andrew asked, do you tend to see more pressure fluctuation or pressure issues with irrigation systems installed with municipal water sources or personal groundwater well sources? So where do you see more of the pressure issues in terms of where the actual water is coming from?
So the simple answer is probably going to be from your pressurized systems, the city supplied water, because we have to keep in mind a lot of people will test their water pressure and their flows, but they'll do that at a time that the community is not watering. So it's critical. Your water pressure from the water municipality can change greatly, especially if you have water windows where people are watering early in the morning. Your pressure is going to be a lot less when there's a lot more demand on the system. So you're probably going to see the biggest fluctuations there. Whereas with the pump's not going to change as long as you look at the pump curve or you have a variable. So yeah, the short answer is a pressurized system because you can't control that. You don't know what everybody else is doing on the system.
That's a great answer, and honestly not what I would have expected. So appreciate that. All right, we're going to take one more question before we hand it off to Alex. This one's from Daniel Overton. And for those of you who have asked questions that we didn't get to, we'll try to get to them toward the end of the webinar here. But Daniel asked, how long does it take, and I love this question, it's very business related, how long does it take to do an audit, and is it a viable, profitable thing to add to the list of services? So Rick, love to know your answer there.
Yeah, I think if that wasn't an easy answer or an easy question to answer, the IA wouldn't have classes and certifications for the audit. I would encourage everybody here to take the audit class. If you haven't, you have no idea all the variables that we deal with. And this is pressure regulation is just one of them. So the easy answer is as much time as you need. An audit, a simple, quick audit just going in can make a huge difference. Like, are the heads upright? Are the heads broken? Do I have the right nozzle? Do I have head-to-head coverage? So an audit can be quick and simple and make some big changes, or an audit can actually take some time where you have to run the various zones and really dial it in. So the easy answer is the more time you put in it, the more you can get out of it.
Yeah, great answer. And I know there are some conservation folks on the call today, and I'm sure they would certainly be in the category of please do more audits. Please make sure that every drop is being utilized to the best of its capability. So love that question, and thank you to Daniel for that. All right, Neil, if you don't mind, let's go ahead and get Alex's slides pulled up, and Alex, we'll toss it over to you.
Okay. Yeah, we can just go ahead and move into that first slide right away. But I mean, I'd like to talk a little bit about kind of the parallels and difference when we're talking about agriculture versus landscape irrigation. The first thing is we're normally dealing with a much larger scale. Rick had said, maybe one zone is dealing with 15 gallons a minute. When we're talking about agriculture, we're talking about maybe a center pivot where it's not 15 gallons a minute, it's 1,500 gallons a minute down one line. And so we're needing to manage that as the pivot moves. So our variables and everything are changing, as across that large scale of irrigation. And that would be mainly the difference. But as far as how it's the same, really hard elevation. We have to know. I hear in the design process, location means elevation, elevation, elevation. You have to know if you're going up hills, down hills, so that you can use your pressure regulation appropriately to make sure that your uniformity is as even as it can possibly be. And we can dive into that first slide of okay. any pivot installation that does not have a reason to not use regulators, we want to use regulators. Anything can change. Any small changes, 10% change to your pressure is, the equivalent of that much change in your flow. Even if you have a perfectly flat field, you just want to make sure that you have that. So anything that any changes made don't change what you're applying to your crops. And to do that, we have to design it properly. Like if our wells fall off, pumps degrade over time. If I want to run this pump for 20 years, it's not going to be doing what it was in at the beginning. Its pressure might fall a little bit. If we're not regulated, our flow is then going to change. But with those regulators, as long as we're supplying enough pressure to make them work, our flow will never change, and our water application will be uniform through the entire machine. And like I said there, when we take all those factors into account, we design it correctly, the irrigation uniformity and the efficiency will improve. We won't be wasting money pumping more than we need to be. It will all work together on that center pivot. And we can go to the next slide. This is just the inside of a pressure regulator, just the very basics of how it works. I know Rick had a slide that basically showed that. I don't want to spend too much time on it. I think we all sort of know how that works. But as the pressure increases on that diaphragm, the spring is pressed on, decreases the flow through that valve, or the size of that valve, it decreasing the flow to maintain the correct pressure. We can go to the next one. So when we're irrigating, we want to be as efficient as we possibly can. And to do that, we have to control everything that we can control, which means limiting variables. So, as this image shows, what are the variables we have here? Primarily, it looks like elevation. This machine is going down a very, very sizable hill. And if we were not regulated, we would have no way to prevent those nozzles from delivering more flow than they should or less flow than they should going up that hill at the end. And so it eliminates very big variables that affect our water application and our efficiency. Next slide. So the variables that we have, these are some examples, there are others. But the things we can't control, topography, the hills in the field, the soil type, we can't control what's there. It's been there for centuries. We can't make a whole lot of difference with that. Climate, we can't choose where we live. We can move, but then we got to deal with stuff everywhere. And we have problems in Nebraska that are different, but similar to problems they have in Arizona. But either way, we're irrigating with center pivot irrigation, and we have our own list of things to deal with. Crops, you can choose what to plant, but in Nebraska, we're planting corn and beans. That's just what we do. In California, we're getting vegetables. In Georgia, we're getting vegetables. It's very different. The things we can control is pretty much the hardware, our scheduling, how much we're applying. But as far as regulation, really what we can control is the hardware. And we can move on to the next slide. So when we try to limit these variables, the first thing, and like I had said, it's elevation, elevation, elevation. That's the first reason why we would need regulators. As that pivot moves, the constant change of requirements of the pressure to make it work. Some fields are flat, some are not. This is just an example that I pulled. In one corner of the field, you're plus 23 feet. And what did Rick say? That's 0.433 PSI for every foot on top of the friction loss and everything that we have going through. So we have to account for that in our design. We have to make sure that at that 23 feet, we can supply enough pressure to those regulators to make sure they work and are effectively regulating our flow through the machine. And we can go to the next one. Elevation change is the most common reason. It's the most common phone call I get, and it's the most difficult phone call because there's really nothing we can do without making drastic changes to either our application or the pump or the well. it gets very expensive to fix it if it hasn't been designed correctly. Valley's charting software for sprinkler charts. It accounts for any hydraulic pressure changes. So as long as it has the correct input with elevation and the right pipe and the right sprinklers and the right regulators, it will give the correct hardware to give a good application. But that has to start at the original design phase. You have to make sure that you have enough to account for these regulators operating correctly, including elevation. You got your friction loss through the pipe, through the fittings, and then you do gain a little bit going down hose drops if you have hose drops on the machine, and it does factor that in as well. And we can go to the next one. Again, that 0.433, this is just another, just hammering home. You have to design knowing that that end pressure has to be enough to account for these regulators, because if there's not enough pressure hitting those, and we'll touch a little bit on those kind of exact specs later, but if there's not enough pressure for the whole machine, those regulators won't open up and you will not get an appropriate or desired water application. Especially at the end of the machine, which is when you're talking about the math of a circle, the last 25% of the machine is about half of your irrigated area, and that's the hardest place to get pressure out to. So if you're good at the end, you're good everywhere else. Yeah, we can go to the next one. And I had talked about, we're removing variables from the equation. If you have pressure regulators and they're operating the way they should, you will not topography is effectively removed. Obviously, you have to worry about a little bit of maybe runoff, but if you're regulated, that's really about all you can do. You can see on that image, if we're going down a hill, those sprinklers will get an increased flow. One of the problems is when we're calculating nozzles with our charting softwares, whether it be one of the sprinkler manufacturers or Valley's, they're not sophisticated enough to know that there is X amount of elevation at 200 feet or X amount of elevation at 400 feet from the pivot point. It just calculates, if you put 20 feet up, it just puts that at the end and it calculates it through the whole thing. And so it's just saying no matter what happens, as long as we pump this much pressure through the machine, the regulators are going to operate and they're going to reduce that flow when necessary to make sure that everything is uniform through the entire machine. And you can see that with the image, the with and without image there. On top of the hill, we can be underwatering because the pressure goes down. And as we go down the hills, we're overwatering because the pressure goes up. And we can move on to the next slide. One of the other things we can't control is the soil types. Pressure regulators will affect the droplet size and how intense that application can be. Sorry, I was just checking on these slides and making sure that I'm in the right spot here. So if our regulators aren't selected correctly, we could get kind of the event we see on the right, that intensive rain or irrigation event. If our regulators are not the appropriate pressure, we could potentially be either putting too much water on a small area, or we could just be too intense with our droplets. The droplets are maybe too big, the soil can't handle that. And so that's one of the smaller things that we have to take into account. Usually the pressure regulators aren't, it would normally be a sprinkler model selection that would change that more. But the regulators do play into that to make sure that you're not distributing water over too small of a wetted area or trying to distribute over too large of an area. And we can go to the next one. The other thing that we can't, or one of the other things I should say we can't control is climate. The temperature and wind, we have to deal with those, and regulators can be a big factor in that. The lower that PSI, it means you're going to get larger droplets, but you will irrigate a smaller area. And so back to that last slide that we had just seen, if you have too low of a PSI, you might be irrigating too intensely because your wetted diameter is too small, or your droplets are too big. The higher PSI, smaller droplets, larger wetted diameter. It's all a balance. You just have to pick which one is the best situation. Sometimes that means multiple different PSI pressure regulators, maybe some 15 PSI and some 10 PSI regulators on the same machine. And we can move to the next one. Uh, when we're talking about large scale irrigation like this, there are often changes in flow. The end guns, the big sprinklers at the end of the machine, those often turn off as the end of the pivot nears a road or another field. They don't want to overlap. So when that end gun turns off, or the corner machine tucks in, or a bender system tucks in and spans shut off and are no longer watering, the pump is now operating at a different point on the pump curve, and so our pressure has changed. If we're not regulated, our flow has now changed. And so the importance of having those sprinklers regulated and designing the machine correctly to make sure that when that corner tucks in or when that end gun shuts off, our pressure isn't spiking so much that we're going to, blow underground pipe. Because those regulators are going to ensure that no more water is allowed out than what those sprinklers are nozzled for. And so it's going to back that pump up, pressure will spike, it could lead to issues. So you want to make sure that in the design stage that that is done correctly the first time. Otherwise, like I had said before, then we have to do well work. We have to buy a new pump. Things can change. Things will have to change at a very expensive, on the expensive side, to fix those issues. And we can go to the next one. Um, as much as I push regulators, there are situations in pivot irrigation to avoid regulators. If we're pumping effluent water or if we're going to have lots of solids in the water, that is a time to consider we may need to um, we may need to avoid them. Or there are filtered regulator options. You'd have to go and change the filters, but at least you'd have to do that less than going and unplugging a regulator or a nozzle. So the regulators are the most likely spot aside from small sprinkler nozzles near the pivot point. They get larger as it goes out and they're covering more area. Uh, but the regulators are the most likely place for the sprinkler package to plug. Comet, Nelson, and Senager, those product lines, they are the center pivot irrigation regulator suppliers that we use. They're always releasing new models, better models of regulators that do uh, that do allow more solids to go through. So it's not as much of a problem as it used to be. However, you still have to keep that in mind. Um, and then, a perfectly flat field with no changes in pump pressure or flow, that would be perfectly fine. That'd be great. That doesn't really exist in a lot of places. I mean, your well and your pump, they're going to degrade over time. I talked about that earlier. It's just you're better in every situation where you can use them. I would recommend them. Even that flat field, they're not that expensive. Even when you're talking about 150 of them or plus on a machine, their list price is not enough for what you'll lose if you don't have them, unless you can't use them due to plugging. And we can go to the next one. And this is just an example of these are the Comet on the left, the yellow, and then Senager in the middle, and then Nelson on the right. To operate, all of these require +5 PSI. So if it's rated for 15 pounds, you need to hit it with 20 pounds of pressure to get it to open up correctly. And so you have to keep that in mind on your design. And like I had said, Valley's V chart keeps that in mind all the way up to that 0.433 per foot of gain down a drop. So 15 PSI, you'd think, well, I need 20 PSI at the end of the line. Well, yeah, but if you have 20 PSI at the end of your pipe and you're gaining 5 pounds going down the drop or whatever, you might only need like 15 or 16. That's kind of getting a little close, and you don't necessarily want to play. Not a lot of margin for error there, but that would be the minimum requirement. We can go to the next one. I say 90% or above of all new valley pivots go out without with pressure regulators. It's probably higher than that. It's probably closer to 99, but I didn't actually go in and do the numbers. I just know from what I see, that's basically what we do. It makes everything predictable and reliable. I trust these products. Our vendors are great. Uh, they back their products. Like I said, they're constantly innovating and designing new things. And I trust them. And if you trust that product to give you that predictability, you're going to have a great time with pivot irrigation. As that pivot moves, like I had said, it's different because you're moving. Your variables are constantly changing, and that can change with landscape as well. As other people are watering and the whole community has their water turned on, things change. But during the course of one irrigation event, pivot irrigation is a very large list of variables, and the regulators makes that list substantially smaller. And that is what I had.
Okay, excellent. Well, Alex, thank you very much. And again, we're going to give Emil a second to switch. We're doing a little musical chairs with our PowerPoints today. So appreciate everyone's bearing with us as we kind of navigate PowerPoint musical chairs. We have 10 minutes. I'd love to get to a few more questions if you guys are comfortable with that. And one of the questions that I think I actually kind of would love to hear an answer from Rick and Alex as well. This question is from Daniel. He asks if the springs ever wear out or lose tension or break. And perhaps that has different answers for various applications. So we'd love to just kind of hear you guys answer in maybe a couple questions how you can maintain your pressure regulated systems, and specifically your pressure regulators, your heads, that sort of thing. So Rick, why don't you start with the answer there, and then we'll hand it off to Alex.
Yeah, the regulator is a component on your system. It is definitely has a life expectancy. This is exactly why we had mentioned earlier the seasonal checks. It's why you need to constantly be evaluating or auditing your system. And a good way of doing that is using those little gauges I talked about. So you do a quick run through of your irrigation zones, and all of a sudden you notice that one of the zones has a lot of atomization, depending on what pressure regulation device you used. So it could be a good indication, or no pressure at all, like Alex had mentioned, maybe that you've gotten debris that's clogged it up. So absolutely, I can't tell you what the life expectancy is for the various brands and makes out there, but if they're not installed within the criteria that they were designed for, it's going to cause premature failure. But yeah, in short, it's a device. It's going to wear out eventually. Alex?
Yeah, that's the same. I mean, let's be real. The ones that we're using in pivot irrigation, they're mostly plastic. They will degrade over time. The higher the pressure that hits them, or the more harsh the water source, heavy iron content, things like that, it will decrease the life of any irrigation component. Um, we usually say 5 years or 10,000 hours is about what you could expect to get out of regulators or just an irrigation a sprinkler package as a whole. Now that depends a lot of quality, water quality, things like that can change that. There's people that can run them for 15 years and they're fine. But at that 5 year mark, other than just the regular yearly maintenance, walking the machine, making sure everything is still attached, that's when I would start to look and say, hey, let's make sure these are working the way they should. And pressure gauges are a good way to test. Do a pressure gauge right after the regulator. You can do a flow test, put a 5 gallon bucket under one of them and measure how long it does over a minute or something like that. Um, just to make sure they're doing what they should.
Yeah, another great question, another great couple of answers there. And the title of this webinar is a deep dive on efficient irrigation, but also the future of pressure regulation in the industry and in pressure regulation specifically. We got a question from Masuma, and I'm sorry if I'm not pronouncing your name correctly, but they ask if there's a new method that can be used for measuring uniformity. So that's a specific question, but I'd love to hear more broadly, both from Rick and Alex, your all's perspective on where we're going in terms of pressure regulation and maybe some of the emerging specific components that are being developed or improvements to practices.
Well, if you want me to start, the industry is obviously concerned about that. I mentioned earlier, we're seeing more and more states that are mandating or requiring by law that your spray heads have to be a pressure regulated spray body. The industry recognizes that. I said earlier, pressure is the biggest variable. It's the biggest thing that we can't control the landscaping a lot, like Alex mentioned. So you're finding on the manufacturing side, we're including more and more components now that have pressure regulation built into them. But again, we know we're designing products and offering features that are being installed and used all over the world. So, and every site is different. So you're starting to see manufacturers where we're offering a device and offer a couple of different pressures. So we're seeing a lot more of the multi-stream, multi-trajectory nozzles. Manufacturers will recommend a lower pressure regulation for your van nozzles, your adjustables, your fixed spray nozzles, and a higher pressure for your multi-stream, multi-trajectory. So it's, we're doing the best we can on the manufacturing side to try and make it a lot simpler to install a system that's going to give you the efficiencies and uniformity, but it's still a system. There's still a lot of variables and changing variables, like Alex had mentioned, that we can't account for on the manufacturing side. Alex, did you have anything to add?
Yeah, I would say, just to speak to that, we're always getting, you said that they're requiring pressure regulators. I mean, that's the same. The NRCS, I mean, does a lot of cost share funding for ag irrigation, and you have to be regulated for that within their parameters. Regulator pressure is also getting lower and lower, as we're trying to be more efficient and decrease pumping costs and use less energy, becoming as green as we can be while still applying the right amount of water. Those pressures are being driven lower. We used to operate sprinklers at 50, 40 PSI. Now we're down to, we have 6-pound regulators, so we can get all the way down that low. And like I said, Comet, Nelson, and Seninger, those brands, they're always innovating. We don't make our own regulators with Valley, but they are always trying to make their sprinkler models operate better at lower pressures. And so that's kind of where the future is going. Lower pressure, higher efficiency.
Yeah, great answers, both of you. Okay, so I just dropped in the chat. We're really close to time, so we're going to have to wrap our questions up. But if we did not get to your question, I encourage you to send me an email, and I'm sure Rick and Alex would be willing to answer some additional questions. But before we do that, I did want to say, Rick, you've got your Irrigation Association instructor polo on. We're a few months out from the irrigation show. Are we going to see you in New Orleans? Thumbs up. We love to see it. Well, for those of you who don't know, we are hosting our next annual trade show in New Orleans in early December. We would love to see everyone there. It's such a wonderful opportunity, not only to participate in sessions just like this, but also to collaborate as an industry. So thank you all very much for joining us today. And again, feel free to send us any emails. And I think Emil just dropped a little information in there about the irrigation show. So again, encourage you to check that out. And thank you on behalf of the association. And Rick and Alex, thank you again sincerely for your time today. We are certainly appreciative. And we hope to see everyone on the next webinar.
Of course. Thanks, everyone.